does seem quite remarkable that we're here 7 years on. And I remember talking to Simon Clayton-Jones about probably 7 years ago, where we thought, well, let's have a conference. And he said, well, nobody would come. You know, what would we do? Why would we want to have this? And it's been a thrill to have been involved in CAS for the last 7 years and be particularly involved in organising our day-to-day. Very grateful for all the people who have put their hands up to speak, to run workshops, to share their experiences of what's happening in their classroom now. We're in a very different place than we were 7 years ago. And it's good that we can learn from each other and build on those experiences and share our ideas in the joint and combined aim of transforming the hearts and minds and lives of the young children who come into our classrooms every day. Because we are all on this journey. No one's cracked it yet. I know within our community and in this room we've got some of the rock stars of computer science. We've got some very, very experienced computer science teachers, but we've got others who I still don't quite know what I'm doing. And that's very important that you feel valued and can still participate in the community. I'm sure Paul takes no introduction. Professor Paul Curzon from Queen Mary University in London, one of the founders of Computing at School. And I know that many of you, it was mentioned in the very first session, have appreciated his rather unique approach to the teaching of computer science, using tools such as magic, looking at stories that he can find just that are out there and putting them into the quite superb Computer Science for Fun magazines and also on the website. We're very grateful. He has a particular skill when he writes and when he communicates and able to make sometimes the most complicated computer science concepts just come to life. So Paul, we're very grateful for the work that you do, often in your own time and off your own back, and often without any funding whatsoever to support us. We love reading your articles and engaging with your website. I'm very much looking forward to your talk this morning. Thank you.
Great, thank you. And I'm glad so many people are using the resources, because it is something I do as my hobby, basically. So the fact that my hobby can be so useful, that's brilliant. So what I'm going to be talking about today is computational thinking. So this is basically one of my passions about how computer science is actually nothing about computing whatsoever. I hate computers. I'm a Luddite. Despite being a computer scientist all my life, I started playing with them from about the age of 14. In fact, I learnt to program before I had my hands on a computer at all on a beach in the south of France, because there was nothing else to do on the beach in Saint-Tropez. And I had a book with programs in and nothing else but a pad of paper and a pencil. So I taught myself to program by writing programs and then kind of executing them in my head, deciding, well, that works, and moving on to the next one. It was then not that long before my dad kind of twigged and managed to scrape together the money to buy me a ZX81 so that I did actually have my hands on a computer. But I've always had this feeling that computer science, you just do not need computers, and it's not about computers. And a lot of what I've been doing ever since is kind of pushing that idea. So I've been teaching programming for, I don't know, 20, 25 years or so at undergraduate level. And the interesting thing is, that's now your job. So what I've been doing has been pushed down, and now you've got to do that to, what, 5-year-olds, 6-year-olds? So it's interesting times for you. But I think it can be done, and it can be a lot of fun, especially if you realise it's nothing to do with computers. So where am I coming from? So you mentioned computer science for fun. So what have I been trying to do with this is basically write up research stories for kids to sort of show what computer science is about and basically inspire people with my passion. So I was inspired at about the age of 14 by Martin Gardner books, which actually claimed to be maths books, recreational maths. And it was only later I realised he'd been lying to me, and it was actually all the interesting stuff anyway in those books was algorithmic stuff. But one of the things that CS Fun's about is the idea about giving really contextually rich stories based on research, leading edge research, that's actually answering this question of why bother to learn computing, why is it important? So I hope CS for Fun over the last 10 years, it is actually our 10th birthday, almost now, to within a week or so in fact. So I hope it's actually inspired people. And if you're not signed up to CS Fun, if you go to the website csfun.org, and go to the teachers section, there's a way you can kind of sign up, and we'll send, well, I can find the money from anywhere, send free class sets to you. So some people just have 1 or 2 copies for themselves, the library, others take whole class sets that they give out to kids. And we'll just send as many as you ask for while I've got the money. And if there's anybody here with lots of money, the grants that I did have kind of run out, so I've got the next year sorted, but after that, any big donors, I'm happy to hear from you. What we've been doing for the last 2 years is sort of switch the focus from producing resources for kids to producing things to help teachers. So we set up this site, Teaching London Computing, which is actually not about teaching London computing, it's about teaching everybody the world computing. It's got that name because we're funded on that at the moment by the Mayor of London, and we felt it would probably be better to kind of get the money if we said it was teaching London computing. But it's basically free resources, and it's me writing up everything I've been doing in schools for the last 10 years, all the sort of activities when I've been doing workshops in schools, gradually writing them up along with some courses and booklets and things. So some of those are in your pack. So it was mentioned, the magic book, which is how to teach computer science through a pack of cards. Everything in the school syllabus, I reckon, is there in your pack of cards. One way or another you can teach it. What I'm going to talk about today is actually one of the other booklets that we've done called Searching to Speak, which is also in your pack. So this is a write-up. I'm going to do a really quick version of it now because I haven't actually got a lot of time, and I'm going to try to pack a lot in. So you can kind of read the slow version here. And this is one of the things we try to do with the booklets. If we do workshops, you've got something to give away to people. And again, these things you can ask for, and we'll send free copies while we've got copies of them to hand out. So that's all on teachinglondоncomputing.org, lots of free activities and other things. So what I'm going to do now, focus on computational thinking. So basically, computational thinking is this kind of term that's just long words to mean something that's pretty straightforward, but the idea is it's what you learn as you learn to program, basically, and you somehow pick it up. I think you can kind of teach it, and especially you can kind of help people understand what it is by stepping away from computers altogether. So what I'm going to do today, I have sort of a couple of different things. One is show how you can get a deeper understanding of computational thinking through Unplugged methods. So I hope I'll give you a deeper understanding of it, whatever level of understanding you've got. But also give you practical ways to teach it, sort of fun ways that you can get this across that anybody can do, because it turns out everybody's known how to do computational thinking since about the age of 5. You all have, just people use different words and you don't never realise. And I want to show how you can embed things in these rich stories, that it's really good to be able to not just say we're learning because that's what the learning objective is, but actually here's a good reason to want to be able to do this. This is why it matters, and that's where the stories come in. And there are activity sheets about the things I'm doing here you can download if you do want to try them out on the Teaching London Computing website. So, that's all intro. What I actually want to get on with is the actual thing. So I thought I'd start with a problem. So computer science, computational thinking is actually about solving problems, and it's solving problems for people. It's not to do with computers. Computers are just a way of kind of making it happen a bit faster or slower because you spend all your time trying to solve the fact that the sound doesn't work or whatever. So here's a problem that is about people that's a really serious problem, because I thought I ought to start with something really serious to kind of make it clear why this is important. So what I'm going to think about is locked-in syndrome. So locked-in syndrome is basically something that could happen to absolutely anybody. If you have a stroke, you might wake up in a hospital bed and you find all you can do is blink one eye at most. You can think and see and hear everything that's going on, but you can't move. It's total paralysis, basically. And in the worst cases, you might not even be able to blink. Okay? So you'll basically end up with this completely intelligent mind in a completely useless body. And people don't recover from locked-in syndrome. There's no cure. That's the rest of your life. So this is about the most horrible thing that I can think happened. And in the media, every so often, there's stories about people going to judges wanting the right to commit suicide. But there's also very uplifting stories from people with locked-in syndrome as well. So one of those uplifting stories is from Jean-Dominique Bauby, and he actually wrote a book about what it was like to have locked-in syndrome. So he was actually the French editor-in-chief of Elle magazine, so the glossy women's magazine. And he was a really successful person, but then he had a stroke. And he did wake up in a hospital bed. He was one of the lucky ones because he could blink one eye, one eyelid. And that was the rest of his life, lying in a hospital bed, only able to blink one eyelid. And despite that, he actually wrote his autobiography from that hospital bed. And it's a perfectly normal book. It's actually described on the front, one of the great books of the century, and that was last century. He wrote it kind of in late 1990s, I think. And the question is, how on earth did he do it? How on earth do you write a book when all you can do is blink one eye? And that's the problem I want to think about. Now, if you wanted to help somebody with locked-in syndrome, then obviously you might think, like a lot of kids do, and certainly their parents, that they ought to become doctors. Maybe they could become nurses, but you could become a computer scientist and help somebody like this. But you could do it without any technology. So technology is something that you could follow up with. But he wrote this book with no technology whatsoever. All he had was one helper, a human person sitting in the corner of his room that he essentially dictated to. So the question is, and we'll get back to perhaps the technology later side of it, but I'm not interested in the technology right now. I'm interested in the computer science, which is much more interesting than the technology. How did he write this book? Okay? So some of you may know there's been a film about it as well. It's sort of very inspirational thing. And actually, I would read this book anyway. It's a really inspirational book about the love of life, basically. Anybody got any ideas, though? How did he write the book? How did you go about solving that problem? Yeah?
It's rid of letters where you can select the scribe has to go across each one of the
right. So you can have something grid of letters, and the scribe, the helper, basically points to them, and when they get to the right one, then how do they know when to stop?
Well, I thought
he blinks, yes. So if you can blink, he can blink at that point. So blink means stop, and that's the letter, and they write the letter down. Now you're forgetting one thing, of course, because the person who's helping can actually speak. So they don't necessarily need a grid of letters even. You could do it even without the grid of letters. And that's actually how he describes it. He describes it in the book how he did it. So basically, the way this book was written was the person who was the helper would speak through the alphabet. So they said A, B, C, D, and so on, until they got to the letter. He would blink and they'd write it down. So the book starts, through the frayed curtains of my window, one glow announces the break of day. How was that written? Well, he started A, B, C, D, E, F, G, so on, S, T. At the point he got to T, blinked, they wrote T down. A, B, C, D, E, F, G, H, he blinked, they wrote the H down, and so on through the whole of this book. And that's how this book was written. And it's not just writing the book, of course, that's how he communicated with the doctors and nurses, with his friends and family when they came to visit, absolutely everything. When he wanted to talk to anybody, that's how he did it. They talked through the alphabet, he blinked, they wrote down a letter, and gradually built up whatever he was trying to communicate. Okay? And so that was his life. And that's basically what the life of people with locked-in syndrome is like. Now, so you remember this, and this is so this is a lesson that will stick in your mind forever. I want everybody, just for a couple of minutes, to try that out. So pair up with the person next to you. It's a good way to introduce yourself to them. So one person gets to blink, thinks of something to tell them. Maybe tell them your middle name that you've never told anybody in your life before or something. The other person goes through the alphabet. Communicate something. So we've got 2 minutes to have a conversation like that. So everybody have a go.
Yeah, exactly. That's fine.
Okay, time's up. So I hope you all managed to have a good conversation and communicated lots of interesting things that way. And I hope now you've got a very clear idea of what it's like and what we're talking about, what the problem is. But especially, what I'm really interested in are what are the problems about making it work. Did anybody come up with problems or things that they realised that the way I just described that isn't enough? You need to know a bit more. What else do you need to make this work? So, yeah.
Blink naturally, so you have to have a code to say the blink will be different.
Yeah, so actually it's very easy to blink when you didn't mean to, you weren't trying to say that letter, and you've got to have some way of dealing with that. And so you can't just say, okay, what you've got to do is A, B, C and blink and that's it, and just blithely go along. And if you haven't worked out something for what happens in advance when you blink and you didn't mean to, you're going to have chaos, basically, because it's going to take a lot to undo it, because for him to communicate, no, I didn't mean that, all he can do is carry on blinking. So it's a lot better if you've worked out in advance that little detail and fixed that little detail. So anybody ideas, how would you fix that detail? You know, what do you do to get around that problem? Yeah?
You'll blink to be a double blink so that you rule out single blinks.
Yeah, so one way would be to have a double blink to actually mean this is actually what I'm doing. You could have double blink meaning undo the last thing. So there were various things that you could do, various choices that would allow that. But you're basically adding to the code that you're using to give you something else to mean that extra thing. So yeah, you've got it.
One problem is the system is being designed by the person who's receiving it, not the person who's transmitting it. So the person can say, I know, we're going to have this system where I go through all the alphabet.
Yeah.
I don't think that's the best system, but I can't communicate that to you very quickly or easily, so I just have to put up with your design.
Yeah, so one of the problems, yes, it's the person, and setting up the system isn't the person who's really got to deal with it. And that's really what we're going to be talking about, or one of the things we're going to be talking about. What are the issues there about getting it right? What that introduces is an idea, a computer science idea actually, of bootstrapping. So you can communicate that. You start with this basic way of doing it, and once you've got the basic way, then you can start blinking. This is a stupid system. Here's a better way of doing it. Can we not? And so on. And then you eventually bootstrap your way to a better system. And that's all bootstrapping really is. Start with a simple way that gets you a way of doing it, and you use that as a way of getting to something better. Okay? And that's the first time actually I've ever given this talk where bootstrapping came up, as it happens, which is one of the great things about these kinds of ways of doing things. Interesting things come up and you go off in interesting directions, and all of them are computer science. Anyway, any other problems or issues or things that people thought of? Yeah?
It struck me that there's a lot of redundancy in the system, so if you know it's English, there's a whole section of the alphabet that's probably not going to follow the letter that you've just used, so you could start excluding letters. So
now you're thinking of better ways of doing it. And that's one. So what he's saying is, actually, once you've started to spell out a series of letters, there'll be whole bunches of letters that just aren't going to come next, so you can just ignore them. So can anybody think of a system that you've used that's predictive texting? Yeah. So what we're saying there is actually you could use a predictive texting kind of system here and actually do the same kind of thing. And he describes that in the book, actually, that they did do that. And actually, he describes it as incredibly frustrating because people would think that predictive texting was a great idea and say, you know, he'd spell out A-N-T-E, and what am I thinking, what word? Exactly. So there were lots of possibilities, but you know, you come up with antelope or whatever, and I was thinking antediluvian or antenatal or something, and I've got to have some way of backtracking all those letters. And that ends up taking a lot more time than if they'd have just been patient and waited. So you've got to be really clear about that and have that as part of your system, your code that says exactly when you accept the word that they've just suggested rather than just them writing it down and carrying on. Okay, so any other points?
Yeah, I've got a colleague with lots of this syndrome, and the method they use is to split the...
I'm going to get to that. That's where we're going, yeah. So this is one of the things I'm sort of looking at ways of getting people to work things out for themselves. So I'm kind of doing this in a way that I hope I'll take everybody with me and you'll be able to see kind of better ways of doing things. Okay. So any other quick improvements? So we'll get back to that improvement later. Yeah. Yes. So maybe you want some kind of system back where he says what he's writing down, or you can see it, or something that you get to see the final thing. Make sure you aren't working with some different system, so some kind of echoing. Yeah. Any other things or improvements? Yeah.
Well, you can do it by frequency of letters.
Yeah. So what about frequency of letters? So actually, he talks about that as well. He's French, so it's not the same as English. So, but in English, does anybody know what the most likely letter that you would be thinking of is? E. And what's the next most likely?
T.
And this is where we find out who works for GCHQ. Can you carry on? Because frequency analysis, which is what we're talking about there, is basically how you crack codes. And basically, this is a separate story, and I haven't got time to tell you about it now. Mary, Queen of Scots, was beheaded because she didn't know enough computer science. Whereas Elizabeth I hired Walsingham, and Walsingham knew enough computer science that actually came from 1,000 years earlier, from originally Indian scholars via Arab scholars kind of knew about this stuff. So computer science goes back a long, long way. Thousands of years people have been doing computer science. But frequency analysis is the reason Mary, Queen of Scots, basically lost her head, and a bunch of other people were hung, drawn and quartered. So it's quite important to be able to do computer science sometimes. But that's another story, I can tell that another time. So back to this, frequency analysis. So what he did it in French, so actually the letters there are E, S, A, R and so on. If you organise the alphabet that way, all the common ones will come up early, and so you'll be able to do it faster. And you know, the Z's and X's stay at the end, and Q's end up at the end, things that aren't going to come up. And so you end up doing it faster. So I better stop now, otherwise we'll not have enough time, and sort of recap about what this is all about. Because what we've been talking about is computer science, and you've all been doing computational thinking there. Because what that was is algorithmic thinking. What have we just described? It's an algorithm. And actually it's a pair of algorithms. It's actually a protocol. It's a way of communicating where the two people have got their own little algorithm that they've got to follow, and if they follow their algorithm, they follow the steps, you do read out ABC and then you do write down the right letter, then the right thing happens. And that's what algorithms are about, that if both parties, all parties, do exactly the instructions without having to worry about what's going on, they don't even have to know why they're writing these letters down, you will communicate the right thing. And that's all an algorithm is. So we've already kind of introduced what an algorithm is, and we've been doing some algorithmic thinking without you even thinking about it. The moment you're starting to think of, but can we do this better? How about predictive texting? How about frequency analysis? How about, you know, whatever other things? All this thinking about the pedantic detail of, oh, we'd better think about what happens if I blink in the wrong space. You want to sort that out in advance, and that's what computer science is really about, being able to see the problems in advance and come up with a solution and tweak your algorithm, tweak the steps, so everybody's doing the right thing so it all works. And you don't get into this situation of, oh God, it's all gone wrong, I'd better get in there and start kind of coming up with new rules to add that will fix the problems I've just seen. That's what happens when people ship software and then they send you a second release and then version 1.2 and then version 1.3. That's because they didn't do enough thinking and they didn't do enough checking and they didn't do enough evaluation. They didn't test it enough, check that it worked. And that's all computational thinking ideas. So we're talking about algorithmic thinking, we're talking about the evaluation of those algorithms. And what is algorithmic thinking? It's seeing the solution of problems as being an algorithm that somebody else can follow. So once somebody's thought this up for Bobby, then you can use the same thing for anybody else with locked-in syndrome. And once somebody's come up with a better system that works for somebody with locked-in syndrome, you can spread that and everybody can use it and it will work for everybody. So it's about, evaluation can be partly about efficiency, it's about coming up with something better, but it's also coming up with something that works for the person that it's meant to work for. So it's lots of stuff going on there that's all about computational thinking, and we're learning some computational thinking, we're thinking about the concepts as we go along. So, then you can get to this last point I've got here, and if I do this with a class, quite often somebody will actually ask this, but how long did it take to write that book? Well, we can work that out with a bit more computational thinking. So, you know, what we could do is sit there and time it, or you know, get people to communicate this way and spend lots of time timing it. But we could also do some thinking to think about it. So, you know, there's 200 odd pages in here. We could count up the number of letters. If we can actually work out how long it takes to communicate one letter, we could work out basically an average for the book. Okay, so we don't actually have to think about the book at all. We can throw that away and just think about one letter. So how long does it take to communicate one letter? Well, we can think about the best case and the worst case. Now, suppose what he was trying to communicate was how much pain he was in, and actually this whole book just went, ah, with lots of A's. So to communicate one A, how many questions do you need to ask? How many letters of the alphabet does the person need to speak before you've communicated that letter A? 1. So the best case is 1. So if we multiply this whole book, how many letters in the book? Count them, multiply that by 1. That's the best it will be to communicate the whole book. It's actually going to be worse than that, but we've got a bound. It's not going to be better than that. Now, the worst case is 26. It could be a Z. He could be saying he just wants to sleep, or talking about bees or something. It goes zzz. And if that's the case, multiply the number of letters in the book by 26, and that's the worst it could be. And so we've got bounds on the answer to that question of how long it takes to write a book, because once we know how many questions, we can say, okay, to ask one question, maybe that's 2 seconds or whatever. We could just time that over several letters and then multiply that by the time. By thinking about how much work, we're able to get a time out of it. And so we can kind of give ourselves this best and worst case. And actually, it's probably worse than 26. One of the problems you didn't point out is you probably want to communicate spaces and commas and full stops and whatever. And actually, somebody invented that. That's where ASCII came from, realizing that you need more characters than just letters of the alphabet. You need capitals, you need beeps and things as well. Apparently, they went into the ASCII character set. And then people realized you need more than you can fit in the character set, and that's where Unicode comes from, if people have come across ASCII and Unicode. So there's lessons in here about character sets as well. And algorithms of how you switch you can get to. But anyway, we can do better than that. Best and worst case, we can actually think about, on average, how long does it take. So, you know, for every A, there's probably a Z. For every B, you know, it's going to balance out. So on average, how many questions do you need actually for a letter? How many letters do you need to read out on average? Not 1, not 26. What's the average? About 13. So somewhere in the middle. So if we multiply the number of letters by 13, we will get an estimate for the whole book. And that will be a pretty good estimate, assuming the letters are fairly uniformly distributed. Now, if we switch to something like frequency analysis, we'll do a bit better, because more often we'll be in the first half of the alphabet, and hardly ever in the other half, so it won't balance out quite half and half. So maybe we'll get down to, on average, 10 questions, or 7 questions or something. And we'll have a better system. And what we're doing, again, is computational thinking. And we're doing abstraction, so we've thrown away details. We don't need to worry about time. We can just think about asking questions. And that's what abstraction is about, hiding details to make things easier to think about. And we're doing evaluation of a different sort, analytical evaluation. We're using logical thinking to think through how much work is needed and giving us a number. And once we've got the number, we can compare different solutions. And when we add in predictive texting, maybe we can kind of work out how much better that makes things, how often that will help, and how much does that shorten things by. And we can compare numbers, and we can decide when somebody comes up with a new algorithm, is it actually better than the ones we've been using so far? And that's where we get to the really interesting thing, because any computer scientist actually knows that you can do far better than this. So we're saying on average 13 questions, worst 26 questions, assuming we're just doing letters of the alphabet lowercase. And you're doing computational thinking as you're thinking of that, but any computer scientist knows you can do better than that. In theory, any computer scientist knows that you should never need more than 5 questions for a problem like this. Okay? So, just out of interest, so don't shout this out because that will ruin it for the rest of my talk. But hands up if you know which 5 questions you need to ask. So quite a few people do. What I'm going to now try and prove to you is everybody in this audience knows the questions, you just don't realise it. And you've known since you were 5. Okay? But to show you that, I've got to switch problems. Okay? So what I'm going to do is switch problems to a different problem, which is the game of 20 questions. So do you know what I mean by 20 questions? I think of a famous person, you've got to work out who I'm thinking of, but I'm only going to answer yes or no. So I am thinking of a famous person. We'll do this fairly quickly. I'm thinking of a famous person. Somebody asked me a question. Male or female? Yes.
Is it
Computer scientists have to be very, very pedantic. So that happens, most times I do this talk, and it's brilliant because it helps you point out why you've got to worry about fine detail as a computer scientist. So would you like to rephrase that? Am I male? Yes.
Are you alive?
Am I alive? No. And what I want you to think about is what kind of questions are you asking? Are they good ones, or could you have asked better ones?
Are you real?
Am I real? Yes.
Are you British?
Am I British? No. Is there perhaps a better question you could have asked for that?
Are you an English native speaker?
English native speaker, yes.
Are you a computer scientist?
Computer scientist, no. I'm not that shallow. Any other ideas? Come on, the primary school kids have got it by now. Northern Hemisphere, and is that a question that would have been better to ask before you asked British and likewise? So that's the kind of thing I'm interested in. Northern Hemisphere, yes.
Were you born after or before 1000 AD?
Why is that a good question is the kind of thing I'm interested in. Was I born after 1000 AD? Yes. Somebody at the back?
Are you famous?
Am I famous? Yes. Somebody had am I a musician? No.
Are you a writer?
Am I a writer? No.
Are you
not what I'm famous for particularly.
Are you a scientist?
Scientist, no. American, yes.
Oh, are you a president?
Were you born?
No. Before 1500? No.
Before 1750?
Before 1750. Now we're locking in the computer scientists and now playing the game, but actually you can do better than the questions you're asking. Probably. It's over here.
Are you Caucasian?
Am I Caucasian? No.
Say the next. She's American.
Am I Martin Luther King? Yes. A round of applause. And actually, I brought a few of them. Hot off the press, the latest issue of the CS Fun magazine might be in your schools already. It's being posted out this week. So yes, I'm Martin Luther King. Don't really care about that and who I am, but what I do care about is the questions you ask. So did you ask the right question first, and why is it a good one or why is it a bad one? So did you ask the right question?
Yeah.
Yes, so why is it good? Yeah, so basically, a lot of mushing there. It's good because whatever the answer, it throws away half the population. You didn't at all ask any single person until you thought I couldn't possibly be thinking of anybody else. So all of the questions were ones that ruled out lots of people, whatever the answer. The best ones, and that's where, are you British? Well, maybe which hemisphere are you in would have been better to ask first. Depends whether you think I can think of anybody other than British people, I suppose. But you're halving. If you ask, is it Martin Luther King first, you throw away one person if you're wrong. You throw away billions if you're right, but are you lottery lucky? How many people here have actually won the lottery? And if you haven't, then you don't ask questions like that. And that's the point. So you don't ask questions like, is it Adele, is it Gandhi, is it Usain Bolt, is it Mo Farah, is it? Because you would be there all night. You would never get there in 20 questions. So instead you ask halving questions. So are they female? Rules out half the population, whatever. So how good is that? Well, let's suppose I might be thinking of 1 million people. A million famous people that we could be starting with. How fast? Well, if you ask questions like that, it would take on average 500,000 questions before you get there. Worst case 1 million, best case 1, but the best case isn't very likely. Okay? So if we're asking these halving questions, how quickly can you get there? Well, let's see. So if I can do this in my head, we're starting with 1 million. After one question, we've halved, so we're down to about 500,000 people left. Another question, 250,000 people left. 125,000 people left. I then make this easy for myself, and this is, you can see why computer scientists like powers of 2. I'll switch to 64,000 people left. It's a bit better than that. 32,000 people left, 16,000 people after another question. What did I just say? 16, 8,000 people, 4,000 people, 2,000 people. After 10 questions, there's only 1,000 people it could possibly be. So let's keep going. 500 people, 250 people, 125 people, about 64 people, 32 people, 16 people, 4 people left, 2 people left, and I think I made a mistake there because I'm running out of figure. Yeah, I knew I can never count in my head. But in 20 questions, you'll find you get down to there's only one person it could be. Guaranteed, not worst case, guaranteed if every question ruled out half of the population. So if you ask perfect questions in 20 questions, you're guaranteed to get the answer in 20 questions. Of course, coming up with perfect questions is not all that easy necessarily, but if you found out that it's a Beatle, you know, one of the group the Beatles, you don't ask, is it Paul, is it Ringo? You ask, are they dead or alive? And you've thrown away 2 of them. And then you just pick one and ask that, and you'll get there guaranteed faster. You might be lucky and get there faster a different way, but if you want guaranteed, then that's the way you do it. So, what we've just discovered is that when I'm thinking of 1,000,000 things, and I've only got 2 responses, yes or no, you can get there in 20 questions. And yet we just said, I'm thinking of 26 letters of the alphabet, and the worst case is 26, and is actually on average 13. So why does it take 13 questions to get through letters of the alphabet, and yet 1,000,000 people I can be thinking of, we can get there in only 20 questions? Something odd's going on there, and it's because we've switched algorithms. You naturally didn't do what we're doing. Is it Adele, is it Gandhi, is it Usain Bolt, is it A, is it B, is it C? And if you put the more famous people at the top and people in the news at the moment, that's a bit like saying, is it E first? And still it could take a long time before you get there. And you didn't even think about doing that. You went straight for the right kind of question. And you would have done from primary school, from the first times of playing this game. So you've known how to do this. You've just got to see the right context and switch over to get to do the right thing. And so you can do this with letters of the alphabet. I won't go through this, but this is actually a decision tree giving you the letters to do. Basically, you've got to ask halving questions. So how can you halve the alphabet? Well, let's just halve the alphabet. You say, is it before N in the alphabet? And then, depending on what they say, you might say, is it before F or is it before T? And actually, as you go through those questions, you get to any letter of the alphabet in 5 questions. And I've optimized E very slightly so you can get to E faster than 5 questions, because I've got a bit of leeway with there being only 26 letters. And so what I've done there is taken something we know from one area and realized I can generalize that and apply it to somewhere completely new and transform the problem and the solution, and we can just pick up that solution and we can now apply it to this new problem. We've got a way of doing it. And that's actually the kind of halving situation that he was talking about, of how it was really done with somebody with locked-in syndrome now. So that wasn't the way Jean-Dominique Bourbet did it. Nobody actually came up with that idea in his hospital amongst his friends, because they were presumably medics, and he was an English, well, not English, it must have been French language graduate, so he knew a lot about language, so he came up with frequency analysis of improvement, but he didn't come up with this as an improvement. And so that's what computer science does for you. That's what computational thinking does. And notice we haven't got any technology here at all. We're still talking about 2 people talking to each other, with no technology in between at all. Computer science is not about technology. You can, of course, then go to eye tracking, brain implants, all sorts of electronics and gadgetry and software and algorithms that are doing all sorts of wonderful things, so you can get rid of the helper. But that's the second step. The first step is get the algorithm right, because even if you're using some special brain tracking stuff or eye tracking, you still don't want it to be slow. And we're talking about slow in the difference between taking 500,000 questions versus taking 20 questions to do something. That's how different it is. So, what we've actually been talking about there, it turns out, is stuff that's in the school syllabus, search algorithms. So we've looked at 2 different algorithms. Linear search is actually 1 by 1. Is it A, is it B, is it C? Variation on binary search. Binary search is splitting things in half. To find something, we're trying to find a name, trying to find a letter, find a way of splitting the set of things you're looking through in half, ruling out half with every question you do. That's all binary search is doing. And More generally, that's a technique called divide and conquer. And divide and conquer is basically, if you've got some big problem, you can make it easier by turning it into a problem half the size that's exactly the same problem, just smaller, and then tackle that problem in the same way by breaking that in half. And that's one of the computational thinking foundations of decomposition. It's a very powerful way of using decomposition to get fast solutions. And here we can use it for halving search, whether it's searching for names, socks, or arrays, or whatever you're searching for. So, does everybody agree, with a bit of computer science, life would have been a lot better for Jean-Dominique Bobby? Do you agree that we would have done better than he got? We could have come up with a better way of doing it. Does everybody agree with that?
Yeah.
Yes. Great, because maybe you're wrong. Maybe you're doing what computer scientists do all the time, and actually we kind of came up at this point right at the beginning, because we're not necessarily thinking about the person. We've come up with a brilliant algorithm, technically perfect, brilliantly efficient, we've evaluated it, and it's wonderful, except it may not work for him at all, because we didn't ask the right question first. And the question we should have found out is things about his abilities and what life's like for him. We didn't ask about whether blinking was easy or hard. So we abstracted our measure of work as being, we've got to cut down the number of questions, but that's the helper asking the questions, and they're perfectly okay for talking through letters of the alphabet. That's not hard for them. It may be slow for them, but it's not hard. Now, if blinking is hard, we've just changed it to taking 5 blinks for him to answer for any letter. Fewer questions, but more blinks. There's trade-offs going off here. So the first thing we needed to ask before we started coming up with this better solution was, how easy is it to blink? And if blinking is hard, maybe his solution was better. Maybe that is actually why he stuck with it. Maybe he did know a bit of computer science, but he also knew what worked and didn't work for him. So they tried it and decided it didn't really work. So we could have made his life better or worse. The other thing I talked about, well, we could throw the helper out of the room and he could just use the technology. That could have made life worse as well. Maybe he came up with this idea of writing the book just because it was an excuse to get a publisher to pay for somebody to sit in his room all day and give him somebody to talk to. And if we've said, oh, we'll stick a camera in the corner and you won't have, and nobody will ever have to come into your room now, you can just communicate that way, that maybe has made his life a lot worse. And again, it depends what's important to him. He can now tweet with the technology there. Is that enough of an offset for people not being in the room as much? You've got to talk to him about it and find out. So this is the main thing. Computing and computational thinking is not just solving problems, it's solving problems for people. Computers are just a way of doing that. And that's one of the main things I want to sort of get across as a sort of lesson of what it's about. It gets missed out. Computational thinking hardly ever mentions people, but it ought to, because it's ultimately all about people. It's about thinking skills. So algorithmic thinking, we've seen some abstraction in this story. Generalizations come across several examples. Predictive texting, we generalized. Frequency analysis from the spies, we generalized and could use that. The game of 20 questions, we've pulled from there, pulling things from one place to another. Lots of evaluation, both testing kind of evaluation, trying it out and seeing it works, but also analytical evaluation, doing it by logical thinking, but also evaluation, remembering it's about people. Does this really work? Is it fit for purpose? And that's what computer scientists, programmers tend to forget. They make sure it works, but they don't make sure it works for people. And that's the solutions for people. And I think I've got 5 minutes left, so I think I'm going to be able to do one last thing, which is show you this. So communicating is about more than just words. So this is a little robot that actually can't understand anything he's saying, but it can just tell the tone of his voice, and then it's reacting to the tone of his voice. So, oops, I hate computers. So he's talking softly and hopefully happy, but then he gets angry.
That's right. Are you getting sad now? Yeah? But stop doing that. That's right. Silly robot. You stupid robot.
And then he'll talk softly and it'll cheer up again, just going from the tone of the voice. So there's communication going on here without words. And watch its eyebrows, it can be surprised in a moment.
Sometimes I've just had enough of you, you silly robot.
And then he'll calm it down and he'll cheer up. So this is just something one of our students did years ago as a final year project. So it's programmed sort of on the laptop to do that. It actually uses a neural network, which is another story as well. But if you wanted to do that with kids, maybe with primary school kids, you could go and buy some Lego kits and try and get them programming Lego Mindstorm to do that. It is just Lego Mindstorm. But maybe you can do it a better way. And to do this, very quickly, just to demonstrate this, I need 6 volunteers. So could I have quickly come out? 1, 2, 3, 3 more volunteers, 4, 5, one more, 6. Okay, so if you want to do in this class, you don't have to have any programming experience whatsoever. This is a great way of introducing programming, basically. So if we can have you two stand at the back, and I need my bits and pieces. I could spend days trying to fiddle with bits of Lego, or I could just say, you're an eyebrow, hold that. You're an eyebrow, hold that. You're an eye, have an eye, have an eye. Okay, and stand in front. Eyes go under eyebrows usually. And you've got 2 choices, so put the other eye behind your back so people can't see it, otherwise we're a monster. And I need one more person. I'm getting up here. Here we are. And then we need 2 people to be a mouth. So here's a mouth, and there you are. And I've just built the Lego. And that was a lot faster, and you don't have to worry about pieces dropping on the floor, except I did. But it's not doing anything because I haven't given it a program. So now we've got to program it. So how do you program a robot to do something as sophisticated as that? It doesn't actually need a lot. You need a few lines of code, basically. So if I program my eyebrow, there's an eyebrow instruction. I don't know my left from my right, so ignore that. That's the left eye, that's the right eye. Oh no, that's the mouth, I dropped them, didn't I? No, I'm getting completely confused. You've ended up with eyes and eyebrows. Bugs going on there. Evaluation, checking programs work. That's it, we're all getting in the right place. They know their left and their right better than I do. And so what the instructions here are things like, if you hear a nice sound for an eyebrow, then you go down. If you hear a sudden sound, then you go up high. And each of them have got sounds like that. You lot have got to do the sounds though. So I need a nasty sound, so you just make up some nasty sound when I ask you to make a nasty sound, the nastiest you can. I need a nice sound. I couldn't possibly comment. You need a nice sound. So it's its birthday, it's just born today, it's 0 today, so we'll sing happy birthday to it for a nice sound. And we need a sudden sound, so I'll count 3 and you shout boo, okay, for a sudden sound. Okay, have you all worked out what you're doing? Mouths are difficult, so eyes are a bit easier, it's just which eye you pull to the front. You've got either up or down or wide open, and you've got it the right way around. Right, we'll see, anyway. Okay, so, on the count of 3, let's start by making it happy. Let's sing happy birthday to it. So, count of 3, 1, 2, 3. Happy birthday to you. Now you've got that the wrong way around. It's the difference between up and down. I'll get back to that. Okay, shh. So what we've just discovered is the ambiguity of English language. That's why you need programming languages, because I said what needed to go up, and I meant the end going up, but the language wasn't clear enough. And that's why we use programming languages, not English, because it's got to be really precise, otherwise it's easy for it to go wrong, and for the computer, the person, to get the wrong thing. So that's put in there intentionally, to allow them to make that mistake. Anyway, so it's a happy robot now. Is it a happy robot? It looks a happy robot. Okay, so let's do the nasty sound. So on the count of 3, the nastiest sound you can think of. 1, 2, 3. And it looks unhappy. And now let's surprise it. So on the count of 3, shout boo. 1, 2, 3. And let's cheer it up again now. We'll finish on a happy note. So sing happy birthday to it again. Happy birthday to you. And it's happening. Okay, and I hope you can see that's exactly what was happening on the video. So thank you very much. Put everything down. It is actually a fun way to introduce programming. You don't have to do it at a computer. You can do that, and we've seen what a program is. And you can get a class of kids to then go into groups of 6, think up new expressions, new sounds, and then add to those 3 lines. So it's 3 lines for each piece. So they just add another line that says, if you hear a shrieking sound, then and each thing does the right thing, and they're writing programs. And I've done this with year 6, and I think you could probably go younger than year 6 with it, and then you could perhaps get them doing it in Scratch or one of these other programs. It would be quite easy once you've programmed it live to then go onto the computers. But it's a lot more fun doing it this way first. And it gets across the ideas, and it gives people things to point to. And it's very communal programming. And you get to test it out, and you're not going to come up front and do it, your version of it, until you've tested it, because you'll look silly if you don't. So it's got this inbuilt desire to evaluate it before you stand up front. So there's evaluation, there's abstraction going on. I don't know whether you noticed, I didn't actually define rules as to what nasty meant or nice. We just used that abstraction of nasty and left it to you. But we could drill down. We could now start writing the rules for what we mean by nasty. Nasty equals Ofsted. Nasty equals whatever, or nasty equals, and you could kind of write that bit of code as well. So there's lots of directions you can take this. I don't have time to sort of go further with that, but that's just to give you an idea. And again, it's starting with a story. The story behind that is, you know, could robots show emotions? Could robots be your friend and they feel like a friend because they react in the same way and seem to understand you? And there's a whole story around that that then goes to the activity and you learn something useful. But embedded in all of that, whatever computing you're doing, is computational thinking going on behind it. And that doesn't need computers at all, and even the computing doesn't need computers either. And at that point, I'll finish. If you want more of this, it's all on the Teaching London Computing website for free, and there's a lot more of books and magazines, and you can sign up to get them sent to your classes. And I'm also doing a couple of workshops later on 2 other sides, the magic and new thing about graphs and whatever. All of these activities as well, they work whatever age group. So even though those workshops are down for Key Stage 2, Key Stage 3, I've done these things to everything up to A level and beyond. It's brilliant kinds of things because they're engaging stories. And the message I really want to get across most is Unplugged is brilliant, but if you embed it in these stories, the why is really important. Getting across that this is something worthwhile learning, it connects to people. That's the really important thing. It's all about understanding people, gives you the stories. And I'm sure I've gone on too long now because Simon's standing there, so I'll shut up. So thank you very much. I hope that was interesting.